You know what? I think we'll just go ahead and start. And I think we have plenty to talk about. Um, Welcome, everybody. This is Open Research Institute. This is our projects meetup focused on FPGA designs. And what we do at this meeting is talk about what we have done, what we have planned to do, if we have any roadblocks that we need help with, and if we need any resources. And the floor is yours, Aaron.
Thank you, Michelle. So last week, I've been working on getting the DVB-S2 encoder ported over to OpenCPI, and I reported last week that I was having issues with the VHDL 2008 and OpenCPI, and a possible temporary workaround until OpenCPI supports 2008 within its build workflow. And I was able to get it to build. I was able to create the Vado block design and then export it with the external inputs and outputs that are required, and then generate the block design wrapper, which then created a design checkpoint with essentially the netlist of the encoder. And I created that as an OpenCPI primitive that was imported into an OpenCPI worker, and then to the hierarchy of OpenCPI's build process. And once it's an application worker, it can be added to an assembly, HDL assembly, and then built against a platform. And I was able to get a bit stream and verify inside the design checkpoint that it instantiated and built out the encoder onto the FPGA fabric. The FPGA that I'm targeting right now is a Xilinx ZCU104. So that's great. I was able to build it, and get past the VHDL 2008 issues I was having. So the next step is to actually use it. So I've been taking Evariste F5 OEO implementation on the Pluto and looking at what registers he touches to get it initialized and started. And then I'll be implementing that logic as well in OpenCPI. So one of the first things it does is initializes the modulators constellation registers. So I'll be implementing the AXE4 light interface. I believe it uses, I'm still digesting it, to initialize those registers and start getting the IP core up and running. So that's what I'll be working on this week. So progress, step in the right direction. So keep you guys updated.
Wow, fantastic and familiar process. And yeah, we're doing
Yeah.
a whole lot of the same in the lab right now in order to bring up the modem and to in a test bench and to walk through a lot of the questions that we had about going from PRBS, kind of a controlled loop back and a very controlled situation, like bringing in data from external from outside. So we we've gone through register setup and getting things initialized multiple times and over the past week and yeah, that's a very familiar process. So really looking forward to hearing how this next part goes. Kind of moving towards the kind of getting it live and getting it lit up. That's a very exciting.
Mhm. Yeah. So on the ZC104, I'm using an FM comms 4, which has an 809364 on it. So a little bit beefier than the Pluto's
Yeah,
809363. Not beefier in the sense, but it's the same family. It's just a
yeah.
little bit slightly different. So that's my goal. And then eventually, once we can work it on there, it can go on the 102, 106. It doesn't really matter at that point. You could just get it with OpenCPI on other
Right.
platforms.
Outstanding. No, I'm
Yeah.
thinking forward just a little bit, and we have a ZCU 102 in the
Mhm.
lab with uh, uh, ADRV. I think it's 9001 or 9001
Mhm.
slash 2, and I can't wait to try this.
Yeah.
It's going to be very cool.
So yeah, actually I ordered an FMC card that has a 93 on it from AliExpress. So we'll see how that works out.
Okay.
And maybe if I get it up and running, I might donate it to ORI so we can have
Oh,
it at working in the lab there as well, not
awesome.
just my computer.
Okay. No, yeah, looking forward to this. This is such amazing stuff. Thank you so much. Anything else you need or any weirdnesses that you need help with or
No, just still digging into it and building it out.
oh, right
Thank
on.
you.
Okay. No, thank you. This is it's fantastic. Very, very groovy. Awesome. Well, hello there. Hello there, Paul. Looks like you're at your remote site. And I think you have lots to tell us. So you have the floor.
Okay, can you hear me okay?
Sure can. Sounds good.
Good. I just got out of a dental appointment, so I didn't have time to drive home for the conference, but I could still get on thanks to my iPad.
Very good.
So here I am in my car. Um, as you may recall from our previous episodes, we're dealing with timing problems in the flow of uh, frames from the encapsulated network interface through the software, which we call Dialogus, uh, and into the through the IIO mechanism that Linux provides on the Pluto to to send stuff, usually samples, but in our case it's not samples, it's data into uh, into the system and then into the modem, which is in the FPGA, and then it will modulate and transmit. And somewhere in that constellation of software and hardware will be the other steps like scrambling for whiteness of spectrum, uh, coding for forward error correction, and so on. Um, so at the moment, we're not doing those last steps. We're just taking the data of the frame and sending it across the internet, the network interface there into the Pluto. Dialogus is uh, padding it out as if it were being forward error correction coded to get to the right number of bits for the actual transmitter. And then the challenge is to get those to the transmitter in a timely way without adding a lot of extra latency for buffering and without ever, ever missing a deadline because the modulator itself has no rubber banding capability. It takes a bit in, puts a bit out, and that's pretty much it. It goes like clockwork regardless. So we've got to keep it fed. And I've known since I first took a look at this software that we're going to need to revamp how time was managed so that there was a window of opportunity to receive a frame from the interface and then stuff it into IIO so that there were always some bits hanging out in the Linux kernel that could be dispensed to the uh, through the DMA interface into the chip in an FPGA. And I had some thoughts about that and some plans and went through several generations of thinking about it, writing it down, working on it. And I had a plan at the beginning of this week that I thought was pretty detailed, and I've implemented that plan. And with only a couple of rounds of debugging, it appears, and this is really a first glance appearance, but it appears at first glance to be working. Um, it's with a long voice transmission, it's sending out a frame every 40 milliseconds, no matter what. And the uncertainty is less than a millisecond. I measured it and I made a little histogram, which will probably be in a publication coming out sometime soon. And that's everything seems to be working the way it's supposed to. Now, there's still some things we need to look at. It looks the spectrum of the voice transmission, which again is not scrambled and not FEC coded, looks very nice. It's smooth and there's no apparent gaps on the spectrum analyzer. But as I think we talked about last week, the spectrum analyzer has a limited refresh rate for looking at that, and it's not very much faster than the frame rate. So it's not really fast enough. So another thing I've achieved since the last time we talked is that uh, have proved that I can use the Maia project, which is another Pluto-based software that's mostly in the FPGA. It's the FPGA running crazy fast, doing everything it can, and providing a network interface to uh, a web browser. And the web browser is running code too, and it's all very nice and quick. And it what it sort of specializes in is broad bandwidth, fast update uh, spectrum analysis and capture. We don't need the broadband, so and I want to see it up close and personal. So I'm changing the parameters from the defaults and from what the real point of the Pluto of the Maia software is, but to get a narrow spectrum and very fast updates. It can update about 2,000 times a second with the parameters that I've chosen. And with that, for these fixes, you could definitely see that there were gaps. There was no ambiguity. Little gaps and big gaps. And the little gaps are completely invisible on the spectrum analyzer. And the big gaps match. They correspond to what we see both in the log file and on the spectrum analyzer. So that's good. I think that means the spectrum analyzer Maia uh, setup is working and giving me the information I need to tell whether I'm really meeting the timing deadlines. I haven't done that test yet since the fix, since I just got it committed this morning. Just got it working last night before bedtime. So there's more testing to be done, but it appears that we're on the track to having a solid transmit capability in Dialogus, and the next steps will be to try to receive it, and as usual. And if that works, then we'll be ready to like do some on the air testing. That'll be a milestone we've been waiting for kind of a long time. Um, in the meantime, we passed through this period of time where we thought we needed, maybe it's still true, uh, some capabilities that the Pluto was not providing. In particular, the Pluto is stuck with this USB interface. That's the only data interface that it's got. So if you want to do a network interface to it, like we're doing, pushing frames through a UDP connection, that's under USB. And that makes it really hard to trace. Um, so there are a couple of different solutions to that. One is to buy a UDP or a USB trace device that goes in the middle between in our case, the Raspberry Pi and the Pluto. And if it can do USB high speed, then you'd be able to capture all the raw USB transmissions at least. And usually these come with software that's sort of like Wireshark, only for USB, that lets you see a trace of all the USB stuff. And the better ones, which unfortunately are also the more expensive ones, then analyze the USB trace and look at it, present it to you at a higher level. So if you had, say, a microphone hooked up, it would show you microphone transactions and not just USB raw transactions. And all this stuff is standardized in what's called USB class support. Uh, and one of the class supports is this, actually several of them, is this Ethernet over USB. Turns out there's at least 3 different ways to do that. One of them is supported by Windows and virtually nobody else. One of them is supported by the Mac OS and virtually nobody else. And the third one, in fact, all 3 of them are supported by modern Linux distros, including the Pluto. Luckily, the people who made the Pluto understood this and made it configurable, so you can use any one of the 3 protocols. And because we're using mostly Macs as our desktops for lab work, we chose the one that works on the Mac and Linux. And for a while there, I was pretty convinced that the problem was in the USB interface. That turns out, I think, now to be wrong, but I stopped that for long enough to actually order a USB tracing device, and that's on the way. It's supposed to arrive tomorrow. The other alternative would be to go to a version of the Pluto that didn't stick only with USB, actually had an Ethernet port on it. And all of the Pluto clones and the Pluto more advanced iterations, even the semi-official ones, they have a gigabit Ethernet. And there are a bunch of them. They're not really very well named. A lot of them are not very well documented. But they usually have in common that they have a gigabit Ethernet. They have an SD card slot, which the Pluto doesn't have. And they may or may not have a bigger FPGA, depending on which exact device you bought. So my other thing that that I did today was pick up the first of two of these that we've ordered. This one is the Libre SDR. It's basically a Pluto, but you can see it's got 4 ports, so it's got both of the transmit receive ports that the Pluto actually has, but doesn't bring out to connectors. They're all 4 of these are brought out to connectors, and then on the other end, look, there's Ethernet. Yay! Um, I bought this based on mostly resemblance to a product that I thought had the necessary uh, yeah, improvements over the Pluto, mainly the Ethernet port. This also has a bigger FPGA in it. That's 7020 instead of 7010. So there's more room for expansion uh, on what goes into the fabric. This I just took out. In fact, I just unboxed it. Here's the bag it came in. Here's the box it came in while sitting in the car here. So I haven't tested this or done anything with it yet. I found out from Evariste that this is probably not the best one to buy because it's the least documented uh, and the least well supported by other software projects. But this is the one we have for now. Coming in the next few days is another one, which is exactly the one that Evariste uses, or at least it appears to be, as best you can tell when you're ordering from AliExpress. So between those two devices, one of which belongs to ORI and the second one is mine personally, we can swap them if that turns out to be handy. Um, we'll have a more advanced Pluto to test with. I don't want that to become a requirement for development, even for FPGA development, if we can possibly avoid it, because the Pluto is reasonably cheap and very easy to get. You just order it from DigiKey and boom, you have it. And they promised to keep making them available for a few years. And ordering random stuff from AliExpress, who knows? I mean, they may be there next week. They may not be. They may look the same on the webpage. It may not be the same product. All sorts of things can go wrong. So I don't want to have our whole process depend on these. But as a lab queen and as another supported device, these could be incredibly useful. The last week, I promised that there would be a written update on what I had done by then, and that's out there. It's been published. You find it on Slack. It's on GitHub. There's an additional document that I created that was the plan for what I've now done to fix up the timeline, and that'll be in the newsletter, hopefully, hopefully coming out soon. And there will be an additional document probably for the next newsletter, or maybe publish it before then because the next newsletter is a ways off, uh, explaining how that worked out and what I have actually done. And with that, I've talked for a long time, and that covers what I know, I think.
Yeah, thank you so much. And just to um, emphasize the gap problem or the latency problem that we were seeing, looks like it's been resolved, and that's really kind of the good news here. I didn't want to bury the lead because there's an awful lot of detail and an awful lot of work that goes into figuring this sort of stuff out. But the achievement is real. And another thing that came out of this was the shutdown and cleaning up of all the threads and making the just general huge step forward and improvement of the software also happened as a result of all this.
Yeah, if I had actually been at home for this call, I would be showing you waterfalls that look like they're supposed to look, except for
Yeah,
there's some spectral features that you can see that'll probably go away, that I expect will go away when we have scrambling. But
right.
that's appears completely smooth without any gaps now, and I'm hoping that Maia experiments will confirm that.
Okay, yeah, looking forward to it. Thank you so much. This is a big deal and very, very appreciated.
Yeah,
Uh,
thank you for your support during all of that experimentation. You've been a big help.
oh, no, happy to. Awesome. All right, I'll show you a brief I've got two images to show. I'm going to attempt to do that right now. Okay, so what you should be seeing is a whole bunch of waveforms from Vivado. And in the process of trying to figure out like why is the transmitter acting weird, I decided that I needed to show the modulator working with external data, because that's what we've shifted to, is instead of just running in PRBS mode, or PRBS is a pseudo random binary sequence. It is a algorithmic way to produce random, like, very, very close to random data. It's super duper useful for setting up your digital circuits, for testing things, for seeing if there's any issues. And we have a PRBS generator, inside the design. And that's what we've been using. And we used it with an internal loopback, never leaves the FPGA, just to make sure that it can figure out what it's saying. The next step up from that is to go outside, all the way to essentially the antenna port, back into the other antenna port, and that's what we call an RF loopback versus a digital loopback. And the RF loopback with PRBS data actually works. And this is extremely exciting. So that's the demonstration that we've been showing, is PRBS generated by one radio is detected over the air by another, and we get 0% error. It's great. Now, next step up from that is arbitrary data that you are sending it, like a dialogus, like interlocutor. What we're doing is from interlocutor, which is the human radio interface, we're taking your microphone and keyboard and whatever data, putting it into frames and sending it off to the modem. If it has an IP address, we can send it, or another computer, or an internet repeater, or whatever. The code that receives this frame in the Pluto or in any modem is dialogus, and that listens on, hey, there's stuff coming in over from this IP address. Wow, looks like a frame. Better send it off to the FPGA. And so that part revealed some potential issues with the way that we have set up the modem. I say potential because we have not yet. We've done a lot of work here over the past week or two, and this is a pretty good summary slide or image of showing like where the status is as of today. So after a whole bunch of initialization, setup, making sure the register writes were correct, making sure that we knew what we were doing, duplicating the success over in the processor side for PRBS, sorted out a lot of things like that. The goal here is to take arbitrary data over AXI transfer. So what we're doing is we're getting data not from PRBS, not from our internal engine, but these are frames, and with all the messiness that entails. So AXI, streaming interface, we're getting all of this data coming in, and we're flowing it through from a different place, and we're not, at least not in simulation, we're not getting coherent data out. So digging in, solve lots of problems, getting a lot closer. It is what the goal here is, like, we need a test bench that duplicates what happens over the air with externally delivered data like you would get in a real deployed system. And we see PRBS over the air working. One of the big next steps with Paul's work and other people working in the lab is to external data with all of the application stuff that we've written lately, try to use the radio and receive with it. And so the work that I've done and that Matthew's done and other folks have done is in anticipation of that, to make sure that there isn't any issues in the HDL. And so far, it's revealed that yes, there might actually be some issues in the HDL. So one of the first things that really kind of stuck, tripping over, is the behavior of the loops. There's two loops, F1 and F2. We have two frequencies. These two tones, there's Costas loops tracking each of them. And we see this sort of behavior here. So in the middle of the screen, sort of the middle bottom, you'll see that there's loop error and loop error underneath the MSK internal recovery section in blue on the left. First, there's carrier phase. So there's carrier phase for F1 and F2. And then there's a loop error for F1 and a loop error for F2. And you can see that it's one or the other. Over time, from left to right, the loop errors only update either one tone or the other. And I'm like, oh, that's pretty strange. Here it is kind of zoomed in. The magenta is the loop error. just to make it very clear that's what we're talking about. You can see that one is updating constantly every tick and the other is just sitting there. What this indicates when you look at these signals, the usual problem is called something called error starvation. So if you have two loops that are kind of competing and correcting, and you can end up with a situation where one loop does a winner take all sort of thing, and then kind of like sides out the other loop, and you don't get any updates. This actually could cause the symptoms that we're seeing, which is in simulation with external uh, data through the AXI path, that we're not actually operating correctly. So that was you got to drill down into the signals and kind of go through the math and kind of look at it really hard. Another symptom that we're seeing is that all the cross products from all the different cosines and sines and integrate and dump, that everything looks really, really good up until about this point. And then the amplitudes just plummet. So I looked into this and I said, well, could this possibly be a true error starvation issue? And yeah, we do go back and forth. Every other clock cycle or every other cycle, the errors are supposed to get updated. I went ahead and changed it and removed that. And I said, everybody gets updated every time. Sure enough, in these waveforms, both loop errors now get updated every time. You can see the updates happen, but the bad news is that the output data, the received data, is still garbage. And it's garbage in a weird way. It's garbage for the first burst, the first few, bytes that you're getting. And then it just settles down into, I have no idea, zero zeros or FS. So error starvation was suspected. It really does sort of look like it, especially when you see something like this, when the loop errors trade off actually being active. And so we have something going on that's a little more interesting than that. And that's where we are as of today. So the goal of this work is to make the test bench in simulation or math land, to make, to go ahead and have a test bench, not just for PRBS mode, but also for external data. We need that. That's something that we're going to ship with the repo. And not working in simulation, let's see if it works in person. Let's see if it works over the air. If we get garbage received data out for otherwise good timing, like all the timing recovery. If you look up here at the top, there's a RX valid or receive data valid signal, and this nice steady tick, 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 tick going on at the top there. That's a sign that there's enough right. There's enough going on really good with the received data coming in over the receiver, over the antenna port, that it's able to extract timing successfully. So there's something going on here in the paths, and we'll just keep digging in. This may we may find out later today, maybe tomorrow, maybe after Germany. But we're well down the path of finding out all sorts of things. The good news is that a whole lot of this is going right. The design is actually performing pretty darn well. And the other kind of thing that we're grappling with is we're still looking at the gains for the proportional and integral controller. So in the end, this may be related to the selection of the gains. All right, that's it for that sort of stuff. This will also be in the newsletter. So we'll do an explanation of what error starvation is, just a basic, like, what the heck is it? Because I've heard of it before, but never actually seen it. And this sure kind of looks like it. And there are situations where the VHDL code is susceptible to error starvation in our design. So it's a really nice way to kind of show in an accessible way what it looks like and why you care, why you want to kind of know about this from a digital logic point of view. Okay, so for our roundtable section, any other reports for Evan or Rick? Anything that you've done over the? Oh, go ahead, Evan. You have the floor.
Hi, I'm building a case for the bit banger radio, RF bit banger. It's a clamshell. I'll have room in it for the a little audio amplifier. so I don't have to twist wires while I'm trying to test it. This is a working radio. I was able to make a call with it, but the signal was a little bit jumbled. Here's the top of the case. I used a drill to drill out the corners, and I'm filing it. And as you can see from the big rectangle, it's going fairly well. And I should have it done before long. Everything I do is so slow these days, but I'm really happy that I'm putting a case on it, and then I can take things a little further. So that's all I have for today. I may hang out for a little while longer.
Right on. Thank you so much.
Oh, thank you. I'll be back, though. I really would like to participate.
Very good. No, thank you. It's a really cool work. And yeah, if you have some photos, maybe you want to share them with the newsletter, that'd be great.
Oh, I'll send them to you first, but yes.
Cool. Yeah, thanks so much.
Thank you.
All right. And yeah, Rick, if you have any reports over the past week, I think probably we're absolutely planning on talking about content that we want to bring, those things that we want to bring to the AMSAT DL symposium about Eve project, and anything that you might want to make us aware of or make sure that we emphasize. And also, I think that you had a trip up to Haswell over the past week too. So the floor's yours.
Yes. Well, we went up to, well, first of all, we had a picnic. Wonderful thing. Paul, the president, declared that we were going to start an annual picnic. And he was kind enough to say that it would be at my house every year. Well, that was interesting. We had a nice gathering of people. Some were members or officers, and some were guests who are interested in DSES. So that went well. Let's see, I went to Haswell, I don't know, a week or so ago. Yeah, a week ago today, wasn't it? And changed out some of the hardware and software modules and collected a couple of days worth of EZRA format data, submitted that for analysis. I did my own analysis. I let Ted, the author of the package, do his analysis, and we were not impressed. Even though I'd made changes that I thought should significantly improve the results, they improved the results of our Galaxy drift scan did improve, but not by a large margin. Not what I was hoping for by any means. So I have swapped out the GNU radio GRC file that does all the capturing and filtering of data before the post-process analysis with the Virgo format capture files, and I captured a couple of days worth of data in this new format with that same hardware change to try to figure out, is this a problem with the GNU radio modules in RZ or EZRA, which it very well may be, because I'm finding some issues relating to the understanding of how the EZRA modules work, whereas the Virgo data collection modules, which record data in a different format with different filtering, are much more well understood. So I submitted those to Dan, who's an expert in that area, but Dan has not responded, and I think it's for the same reason that he didn't come to the picnic. He's busy somewhere doing something. I don't know what. So I said, okay, this morning I'm going to do my own Virgo analysis. So I said, okay, but Virgo is Linux only. So I'm firing up. First thing I do is fire up my VMware Workstation Pro, find out that that's got to be updated, And the automatic updates don't work anymore because Broadcom has screwed up VMware pretty badly. And it took me an hour this morning to figure out how to update it. I finally did successfully, got on my Ubuntu and found out that needs to be updated. And I'm saying, and it's telling me right now all the various ways that I have screwed up. And so I'm updating that. Eventually, sometime during the day, I will download the latest Virgo modules into Ubuntu and try to run them against that data to find out if the hardware down there is the problem or if it's the data collection portion of the software modules. Most of the focus on all these software modules is in the analysis section, and people often leave, just assume that all the data collection is being done correctly. And yet, when you look at the module set in GNU Radio, they're extremely complicated. And I said, wait a minute, if they don't understand what they're doing and they're very complicated set of modules, something is wrong here. So I'm focusing on that at the moment. I'm really anxious to get to the point where this becomes just a routine data collection because we have about 40, because the antenna is so big, it only has a 1-degree beam width. And we want to go from plus to minus 20 degrees from vertical in order to completely map the universe. And we only go there once every couple of weeks. That's 40 couple of weekses. So I'm very anxious to get past all these technical difficulties so that we can start recording all this data. Most people record hydrogen drift scan data with 10-foot dishes. And so they don't have to do it 40 times. They can get a complete scan, in like a dozen times or less. But anyway, that's where I'm at. A little frustrating because what I'd really like to be doing is working with you on the FPGA stuff.
Oh, don't worry. That there'll be plenty of work when you're done. You forgot you have to update Virgo. You'll find out that Virgo is no longer somehow compatible with the data format that you were using.
I'm just gonna.
I mean, because this is such a familiar. You're singing the song of our people.
I know this is.
So don't worry. Don't worry. The FPGA work will absolutely be there. We actually have one of the items on the agenda that we haven't touched yet is the way that we designed and implemented the minimum shift key modem was following the original these really a set of really neat papers from more than a couple of decades ago. And this is Massey and Hodgart, the folks most responsible for this batch of academic work papers trying to explain like, okay, here is how you do this cool modulation. And it's an older design, sure. So it uses two separate Costas loops, one for F1 and one for F2, and uh, a number, of things about this is really neat. However, one of our volunteers said, that isn't the way that we do things these days. You generally, well, everybody has a single NCO, and it's one loop that it goes back and forth looking at the two different tones. So it would be a step forward to have this a more modern design. Now, there's a lot to be said for implementing something that's documented this way, that back in the day already flew into space and is, and we are putting this design out there. There are very few to none other implementations, open source implementations of this sort of work. But we absolutely hear this. So it, as soon as our current implementation sort of kind of performs equally well in over the air external data, whatever that problem turns out to be, as soon as it performs as well for that as it does for the PRBS, the internal generation mode, then I think we're in a really good place to take full advantage of our modular approach to design. And that's why you do this, so that you can say, okay, this part of the design, let's swap it out for something else. Let's go ahead and see how this will work with, you have this old design or older design, some of a classic design from the papers, the updated way of doing things in modems. And we're actually able to do that. So that alone is a whole pile of work. So if that appeals to you, then we got plenty of that. And there's a whole other neat, really set of work coming in the FPGA when it comes to forward error correction. Because as Paul mentioned in his report, right now we're just kind of dummying up the number of bytes, 271 bytes to a frame. It's 134 bytes of just the data. Like when you make a frame from interlocutor, it's 134 bytes of data. That's the frame. And then when it goes through scrambling, whitening, and forward error correction, and then you add the sync, the sync pulse or the sync frame on it. Wow, it's now 271. Okay, so a big part of that is the error correction. We have different error correction for the header because you need to get that decoded quicker, so that's the header is like that tells you a lot. And then the payload is left to be a different. So the traditional way of doing this is to have like a Golay style block encoder on the header. And then something like a convolutional encoder for the payload. Just a lot of so yeah, that's the baseline design. The modular approach to this allows you to swap in different forward error correction, and so we have plenty of things to work with here. Matthew's very interested in spinal codes, which I didn't know anything about until we brought them up, and they look pretty neat. So for the payload, a spinal code versus a traditional 2/3 convolutional code. And the way that we have it, since it's a modular design, you can actually have a pretty straightforward, that's in air quotes, because as you have just described, things are never truly straightforward. There's lots of things have to happen. But, with a modular design and enforcing that discipline, then we have a way to say, okay, here you go, convolutional versus spinal, or whatever forward error correction folks want to play with. With like DVB, you see the same sort of thing. The physical layer header in DVB-S2 is encoded with Pyro2 BPSK. It's a booming thing that comes right through. Like, can't miss it, because you really, really need the physical layer header information to extract everything in order to make use of the rest of the payload, which may be a much higher modulation encoding, depending on your signal to noise ratio. But, the effort is to make sure that you have the physical layer header so that you know what you're dealing with. So all of that stuff is in the future. So please don't feel like you're missing out. And please understand that we have absolutely all the empathy in the world for the updates and why doesn't it work? It worked 2 months ago and I ran the exact same script and now it's puking marbles. So this is, yeah. It really is the song of the people. And no, the drift scan thing, everybody I've told this about, they're really super excited because they understand. Like, you can explain it to an enthusiast, like, and they get it. They go, "Oh, that's really neat." And this is a really big dish. So it's it's like you said, it's larger than the ones that usually do drift scans. And I think that the potential for some really interesting data sets is very high. And yes, some of the setup and what you're dealing with is going to be painful. Something that I think might help is if you go ahead and do the photogrammetry of the surface of the dish so that that RMS error can actually be determined. And once you actually know that, then you can tell what's a real limit, like what's a real physical limit of the dish versus what is a limit of all of the DSP stuff, the software, the radio. So I don't know. I'm going to advocate for prioritizing that experiment. It will take a weekend to do. You will have to, you know, practice ahead of time and then set it up. But it's a really inexpensive way to get a very important um, result. And the only other way that I know how to do it is to just go ahead and have an experiment where you can somehow then back your way into the noise temperature to get an actual noise temperature for the dish. That'll only give you 1 point at one particular time. If you actually get the physical RMS difference in the surface of the dish, then that goes into the equations that can then generate any link for you. So it's a much better way of doing it, but it will take like a weekend to do. Anyway, back to you.
So we also had a highly successful visit a few weeks ago where we set aside the drift scan for a day, and we wanted to detect the weakest pulsar we've ever detected. So we went after the crab pulsar, and I'd like to, if I can, show you the result. I'm not going to try to explain it. That's Dan's area of expertise, but I think you'll get the point. This is the pulses from the crab pulsar at 33 millisecond rep rate for this pulsar. It's the fastest pulsar we've ever tried to capture. And I think you'll see from these pictures that we got a very solid response. This is, of course, after all the post-processing, and this is the Virgo software. So I thought that was pretty exciting. It helped to validate that most things on the dish are working pretty well.
Outstanding.
The signal strength of this was 550 millijanskis. For those of you who understand what that means, we're talking signal strengths significantly below what you're working with.
Yeah, very much
yeah,
so. That's outstanding. Yeah. That's a really, really good result.
It is a fantastic result. Now for that particular pulsar, we discovered that that pulsar is much stronger at lower frequencies than at higher frequencies. So that was done, I think, around 387 megahertz, if I recall correctly. And it was done using a V210 SDR synchronized to a your GPS 10 megahertz, a super one, but learned a lot on this one because there's a tremendous amount of drift, and we weren't at first sure what all that phase drift was about, but I think we're learning a lot. So every now and then we take the drift scan down to do a focused experiment for a day and then just turn it back on. And it doesn't affect the drift scan results at all. They don't mind. So
outstanding. That's really, really cool.
Yeah, I'm very pleased. So what I want to do, I'm thinking that the next I just received today some of the new gain blocks that I had ordered weeks ago. Usually they come in a day or two, and I don't know why it took so long for them to arrive, but so I'm talking to Paul and Ray about another trip to Haswell, maybe this week. We never go without 3 or 4 or 5 things to do. And I'm thinking seriously about swapping out the low end SDRs with a B210, which is way overkill for drift scan, and just do it because there's a lot more information about how to capture data with a B210 than almost any other thing out there in the GNU radio world, even though it's a very expensive way to collect data. So
Yep.
I don't know if that's the right move or the wrong move, but I'm having trouble with GNU radio modules saying that they can control the RF gain of these receiver SDRs, which have RF gain control capability, and then seeing in real time on the spectral scope that that's not doing anything.
Right.
And I'm getting frustrated with that, and I'm figuring, well, the B210 is maybe the right way to go, just because I don't want to fool with this anymore.
Right.
Just,
I mean, it's the right tool for the job. It's okay to have some overkill.
yeah, I mean, it's sort of like, a 16-inch shell instead of a 50 caliber shell, but what the hell?
Right.
And
It's
I
the
don't
right
know.
answer.
If I do go to have, see, I wanted to get this Virgo data analyzed first to see whether the SDR, what is it? It's an SDR play, or I get it mixed up. Yeah, SDR play is what we're using, whether that's okay or not. So I was going to rush through the Virgo analysis because Dan's not available, see what happens.
Yeah. See, Linux can tell when you're in a rush.
Linux just did thousands of lines of Linux updates.
Yep.
I wonder if I
Tell when you're
broke.
in a hurry, and it's like, oh, are you in a hurry?
The good news is this Ubuntu is a virtual machine. It's trashable if I make a
That's right.
mistake.
You can take it out back and shoot it. That's right.
Yeah.
Yeah.
Oh wow.
I know. It's empathy. That's all I've got for you, man.
Oh, and if you need more sources of empathy, over there is my Agilent spectrum analyzer, which gave up the ghost a few weeks ago. And I opened it up and said, "Oh, I must need a new one of these boards." So I ordered one on eBay, and that didn't quite do it. But then I noticed all the LEDs on the power supply were not lit. Well, all but one were lit, but the one plus 15 volts not lit. So I said, "Oh, okay, I got a bad power supply." And sure enough, test point said no 15 volts anywhere. So I ordered a new power supply and got the new power supply, plugged it in, same thing. I said, wait a minute, that can't be the same failure. So I started pulling boards out, and sure enough, the power supplies were both fine. The board that I had ordered was shorting out the plus 15. So I said, wait a minute, I got two of those. They can't both be shorting out the plus 15, but they were. And I said, wait a minute, it's got to be one of these wires that plugs into the boards. So Ray comes over for the picnic. After the picnic, we start looking at this and we start plugging and unplugging wires. Now I've got it to the point where, guess what? I've got all the power supplies back and all the boards. Doesn't matter which board you plug in, it doesn't short out the power supply anymore. And doesn't matter which power supply you use, they both work. Everything works. But the spectrum analyzer is back to the original problem. It still doesn't work.
Right.
Go ahead. Tell me about frustration
Yeah.
and
Yeah.
difficulty. Simple stuff.
That's right.
But oh, I
Yeah.
bought a new toy that might be interesting because I've always wanted a really good signal generator, and I've always had a signal generator, but not a really good one. Now I got a really good one. It's an Agilent something. Well, the number probably wouldn't mean anything to you, I suppose, but it's the previous generation of what they're selling today. So it is not for sale new anymore, but it's the one that was for sale before this. So it's not very old, and it's a 0 to 6 gigahertz with all the fancy features, but it's a vector signal generator with I and Q inputs.
Oh, very good.
So if you give me something that generates I and Q, I can put it out on any frequency and it's also the high power version.
Oh,
So
very
I
good.
can put it out at plus 20 dBm. Uh,
Okay. No, that's good because the over the next year or so, I think that we're going to be trying out a lot of signals for things like Eve, and we'll need to go ahead and do some experiments with all sorts of amazing uh, modulations and encodings. So I'm really looking forward to that.
it's I haven't a clue how to use it.
It's okay. There's time.
The operator's manual alone is, I don't know, 500 pages,
Yeah. No, the modern test equipment is it's pretty amazing. Um, because a lot of test equipment has actually been replaced by software-defined radios. Like when Paul was talking about using Maia as a spectrum analyzer, it's really, really good at that and has proven to be useful multiple times. But that's not the case for everything. Um, so we're in a very interesting time. We're living through a very interesting time of the big changes in like radio and test equipment and accessibility. And it comes with some sharp edges though, and some discontinuities. Uh, and yeah,
Well,
500 page manual. Yeah, that that sounds about right.
I've got all the little, $300 spectrum analyzers and VMAs and all that, and they work remarkably well. My big test equipment works maybe 10 dB further down,
Yeah,
but 99% of the time you don't need that.
true.
So I carry the little ones in my uh, electronics case as well every time I go. So I've always got a VNA spectrum analyzer signal source of some sort and so
Yeah,
forth.
cool.
Whenever I,
Oh, sounds amazing. I think this is really, really neat. Let me let me close up with a few little items. Ed Friesma has finished his application for the phaser project. This is sort of a contest going on that involves the analog devices phaser. The phaser is to the phased array world what the Pluto SDR is to us. It's about 10 times as expensive as a Pluto because it's a phased array. But what this effort is about is trying to use the analog devices phaser in a kind of a new, innovative, interesting way. So the application to participate in this activity is then sent off, and we're looking forward to hopefully it being successful and being able to get hardware for this. And our goal is to set it up so you have a phaser and you fly it on a drone, and what you're doing is you're characterizing 10 gigahertz radar. So what you're doing is you're actually characterizing radar installations. So that's kind of the proposed goal. We're kind of hoping that perhaps maybe some weather radar folks might want to let us experiment and to so that they can get some good data on the performance of their radar. And I'm sure we can come up with some other things. So that application has been, proposal has been sent off. We have our late summer newsletter coming out imminently. So if you have updates for that or want to share things for the newsletter, please go ahead and send it in. And of course, there'll be another one in about a month after that. So don't feel like if you missed out this time around, it doesn't you can't participate. Always participate in outreach and publications. Will help you achieve your goals there. And I think that wraps it up. We are going to be discussing the EVE Earth Venus Earth 2026 attempt coming right up next week or two is the AMSAT Germany Symposium or AMSAT DL Symposium. And there's also a Future Geo workshop the Friday before. So we're going to be bringing all of the work that we do and kind of like summarizing our opinions about where the future of amateur radio and open source digital radio should go. And we will be discussing our efforts to kind of come up with, what we call a link budget or a link analysis document, what we know about the link and what we think, what signals we think will be able to close this link to transmit data. So we already know, and it's been done at least twice, that we can get a carrier wave bounced off of Venus and detected. Now the next step is to turn that detection of just the carrier wave into a communications channel to like what can you expect, what can you do, what kind of equipment you need. So those are the sorts of discussions that we will have along with all of the other amateur satellite discussions at AMSAT Symposium coming right up. So that'll take us to the end of September, and then we will be back. We'll be at Pacificon and sharing our work and talking about Ribbit and RF Bitbanger and all sorts of stuff that we do. So if you're at Pacificon, please know that we'll be there and find us. I'm not sure if we'll have a dedicated booth or if we'll be with one of the other clubs, but definitely be speaking during Pacificon. So looking forward to the Q&A and all that. And that wraps it up for the week. Thank you everybody so much for your time and all of the hard work. Everything that you're doing is so appreciated. And please reach out if you have any roadblocks or need any help, need any resources, have any questions, or just to share the stuff that you're doing. We would really like to be able to make sure that folks know about all your work. All right, any last questions or comments before we close for the week?
I've got one.
Go ahead.
I'd like to point out that the remote lab also has this capability that Rick was talking about to transmit on any frequency from IQ samples. And it also has the property that we haven't figured out how to use it yet. But we'll be getting there. Ours is a Rigol because all of our stuff is Rigol apparently. And on a related subject, another thing that Evariste told me or pointed out to me is that it'd be really nice to capture scenario of packets maybe on that simulated Ethernet and be able to replay it as part of an automated test. And that's a good idea. And I'll be looking into that too. I found out while we were sitting here that there's open source software called TCP Replay that can play back a PCAP file. So I capture it with Wireshark and play it back repeatedly. That'll be cool.
Right on. Thank you.
I forgot to mention that signal generator has Ethernet, native Ethernet.
So does the Rigol.
And it can take a file up to the size of the internal RAM, which I'm not sure how big that is, and just stuff it in there, a bunch of INQ stuff, and make these repeatable IQ playbacks through the RF. I'm not sure what that's all about, but it's also remote controllable, so it makes for a nice piece of lab gear if you're remoting in. I haven't punched a hole in the firewall to allow that, but yeah, I was going to buy the Rigol, but I think the equivalent Rigol to this one was actually more expensive than this, and this was very expensive.
Ours is probably a lesser model.
High-end stuff,
Yeah.
they actually charge real money.
Yeah. They do. Very cool. All right, everybody. Thank you so much. I think that just keep an eye out for any announcements for meetings for the next couple of weeks because of the amount of travel and the amount of discussions and presentations going on that we may we may not be meeting at this exact time. But just keep an eye out, and we'll see you next time. And please reach out on Slack or email if you need anything. And thank you, everybody, for all the amazing work that you're doing. See you soon.
Thank you.